Morning. So I thought I'd take a second to just do a little bit of follow-up with regards to the energy lab that most of you guys were able to submit last week. And really, I mean, honestly, a really, really good job on those for the most part. I thought you guys navigated through some of the pre-lab and post-lab questions really well. And you did a great job kind of collecting good, solid data. So I wanted to at least talk about maybe one or two kind of small issues with the data analysis, and then even just talk about what's kind of some big take homes for the lab if we're still having a hard time with that. So this will be worth your watch. It shouldn't be too long. First off, one of the things we always want to remember to do when we are um, collecting data and trying to figure out how to analyze data like that is when we graph two variables as they relate to each other, we really want to graph those individual points. And the hope is that most of you were able to graph on the bottom. This is our number of bounces. And here we have our height. And this could be in whatever units you kind of choose. That's up to you. But you should have hopefully seen something like this for most of your data. And depending on how much data you had, obviously you're going to have more points or less points, and that's going to be more pronounced. But you should end up with some sort of a exponential decaying curve. Now, a good number of us actually never graphed the points at all. We just kind of had it connect the dots, and we got weird looking lines. Let's stay away from that. We can always take the points that we graph and fit those to a line or a curve. We had a couple people that graphed these points and then made like a linear trend line, which looked like that. And it's like that doesn't fit at all. That didn't make a whole lot of sense. But just make sure that our analysis of the data, so that means when we graph it, how we fit it to a curve or a line, that analysis makes sense. Because if someone's reading through your report and they see these data points that look like that, and they see a trend line that comes across maybe right there, they're going to say, this Yahoo has no idea what they're talking about. Why am I even wasting my time reading this? So we want to make sure these things fit, these things mesh. But what we see here is, one, we don't see the same amount of energy lost each time. And part of the reason why that is because every bounce, there's less total energy to lose. So if you think about exponential decay is basically a percentage of the energy being lost each time. I'm not sure if you guys went through and calculated that, but my guess is you would get a similar percentage drop from here to here as you would get from here to there, as you would get from here to there, and they would always be a similar percentage, maybe 30%, maybe 40%, maybe even 50% or 60%, depending on the ball you drop, depending on what surface it bounced on. But you'd see that same percentage drop every single time. Now, the real question is, what happens to that energy? Where does it go? Well, we'd love to think that mechanical energy, that would be gravitational potential, kinetic energy, and elastic potential energy. We'd love to think that those three forms of energy can be greatly conserved in a situation like that. But they're just some factors that tend to zap energy away. There's always this energy cost, the rake, as we call it. And a lot of that ends up being thermal energy. So you're going to have energy dissipated when these objects fall through the air, and that pushes air molecules out of the way and makes the air molecules move. Well, that's transferring kinetic energy not to the ball, but it's to these air molecules to create wind currents that you might not be able to feel, but it's still energy. You're also going to heat up the air molecules. Thermal energy is a huge source. So we have other kinetic, right? We have thermal energy. It's a huge source of waste. Huge source of waste. So where do we get this thermal energy from? Well, any friction, any movement, any contact, it's always going to produce some levels of heat, right? When your ball compresses on the ground, all those molecules tend to move around and shift a little bit, and that's going to be a huge source of thermal energy. Some objects obviously can compress and bounce back really well. Some objects, that compression process causes them to lose a whole lot of their energy, just depending on how those molecules and compounds and atoms are all set up. You hear the ball bouncing, right? So when we hear something, sound is actually just a vibration of molecules. And so when we hit the floor, that vibrates the floor and that sends vibrations and these sound waves throughout the air molecules. And that's a lot of basically kinetic energy that's not going to make the ball bounce up. It's going to make the floors and the walls vibrate. It's going to make the air vibrate. So we have sound as a huge source of kind of energy suck out of our system. And so kind of these three main ones, I would say, combine to form kind of the total amount of this kind of energy dissipation. And so ideally, we'd like to think that our energy is conserved from bounce to bounce, but we see it never gets back to the same height as it was before. And a lot of that is because we have energy that gets converted into wasted kinetic heat or thermal energy. And then we have the sound or propagation, vibration of things. And there could be probably other ones that you could think of. But those are kind of the main places where this energy tends to go, rather than hanging out with our ball that we've dropped and that being a source. Okay, so just think about that. Big take homes. We're going to start doing some problems today that are of the assumption that we could bounce this ball and it would bounce back to the same height every time. So we're going to try to avoid or ignore any of these sources of kind of energy dissipation. We're going to say, you know what, the rate just isn't going to happen, or it's going to be so small here that we're just going to ignore the fact that any energy goes anywhere else. And we're going to live in this world where energy truly is conserved from start to finish. And so we'll look at some mathematical benefits and things we can mathematically kind of conclude and deduce based on that, if we kind of make some not super accurate, but mathematically, quantitatively accurate assessments of what happens to our energy during this. Hope that helps. Again, really nice job on that lab. Continue to remember that data is so important. So the amount of data we collect, the quality of data we collect, how we present that data, and what we say that data means. Okay, so those of you guys that really missed the mark on that, did not present your data well, did not understand the data you were presenting. And that's obviously a huge issue. I'd rather you get some help, talk to some people, talk to me, and understand the information you're giving me on a lab report than just throw stuff up there and not really have any idea of what you're trying to show, or more importantly, why you're trying to show it, because then we don't learn anything out of it. So yeah, that's that. I'll put this up on YouTube and you can have this, but definitely take a look at this sometime this week.